For our last section, we're going to be talking about solving polynomial and rational inequalities. So at the very beginning of this class, we talked about solving linear equations, and then we talked about linear inequalities. We're going to do the same thing now for polynomial and rational equations and then inequalities. So recently in section 3, or unit 3, we talked about solving polynomial equations and solving rational equations. And now we're going to talk about the inequality version. So examples of inequalities like this look like saying when is a polynomial bigger than 0 or when is a polynomial less than some number. Those are examples of the inequalities that we want to solve. So we want to be able to talk about when a given polynomial or a given rational expression is something like positive or negative or whatever. So if we know what the graph looks like, so if we have a graph like we have over here, then we can answer the question relatively easily. So here we could say, well, f of x is bigger than 0 wherever its y value is bigger than or equal to 0, and that happens in the green region for this graph. So the answer for this first one would be the interval from -1 to 0, together with the interval from 1 to infinity. So those are all of the x values that would give you a y value that's bigger than or equal to 0, because this set of points is the set of points that has positive y values. Similarly, the red parts of the graph correspond to having negative y values. Now notice there is a slight difference between asking for a non-strict inequality and a strict inequality to hold. If you have a non-strict inequality like this top one, then you will include the zeros. So the top inequality is happy with allowing f of x to equal 0, and that means you would include these endpoints like I have in that top set of intervals, because those are the zeros of f. And in the second inequality, we want strict inequality. So we want f of x to be a strictly negative number. So whenever you have strict inequalities like this, then we only want the places where it actually spits out negative y values rather than allowing the zeros. So here I would have the interval from -infinity to -1, together with the interval from 0 to 1, but this time I would not be including the endpoints because I don't want to allow f of x to equal 0. Here I just want the y values to be strictly less than 0. So in this section, we're going to talk about how to find answers like the ones that I just found without having to know what the graph looks like. And our strategy for doing this is to first notice that if you look at the sign changes, so where we go from negative to positive or positive to negative or whatever, then notice that all of the sign changes have to happen at zeros of f when you're looking at the graph of a polynomial. So what we're going to do is we'll first decide where the sign could be changing. And we will do that by just plotting on a number line. So this will be our x number line. We'll plot all of the zeros of f. So I would plot -1, 0, and 1. And we know how to find the zeros of a polynomial already. So we start by just finding the zeros. And then what we know is that on each of these intermediate intervals, on each of these 4 intervals, the sign for f is going to be either positive or negative that whole time, because the only time that f is allowed to change sign is at these 3 points. So notice that if we look on this left interval here, then the sign for f of x is always going to be negative. So here the sign for f would be negative. But if I look between -1 and 0, there f is positive. And then the sign changes to negative again, and then the sign changes to positive again. So this is what's called a sign chart for f of x. So this is a sign chart. And this is what we're going to be making in this section to figure out when a polynomial or when a rational function satisfies a certain inequality. So if I wanted to know the regions on which f was positive, I would just have to look at this sign chart and say that it's positive here and here, for example. And then I could write those regions in terms of interval notation like I have up at the top here. So that's what we're doing in this section. We're going to be working on building a sign chart like this. And let's work through an example. So here we want to find the intervals where x squared is bigger than 9. So our goal is going to be to figure out where this expression is bigger than or equal to 9, but the strategy that I talked through up above requires us to talk about where the sign changes, so where we go from a positive to a negative or vice versa. So our first step in these problems is just to rearrange everything so that it lives on one side of the inequality, and we have a 0 on the other side. So the first thing that I would do is I would subtract 9 from both sides here, and I would get the new equivalent inequality that x squared minus 9 is bigger than or equal to 0. And now let me call this left-hand side, I'll just call that f of x. So now this is rewritten so that it's like the question that I asked at the beginning here. So I just want to know, when is this f of x bigger than or equal to 0? And for this, what we're going to do is we'll first figure out when f is equal to 0. So we will start by setting x squared minus 9 equal to 0. So maybe let me break this into steps. Our first step was just to rewrite it so that f lives on one side and we have a 0 on the other side. Our second step is going to be to find the zeros of that function f. So if I have x squared minus 9 is equal to 0, then I could factor that left side if I wanted to as an x minus 3 times an x plus 3 equals 0. And then I can just read off the roots from those two linear factors. I see that x needs to be plus or minus 3. So I find the roots of f. And then what I do as my next step is I put them on the number line like I formed earlier. So I know that negative 3 and positive 3 are going to be where f is equal to 0. And that means that on each of these three other intervals, f is going to be either positive or negative. So our goal now is just to determine whether f is positive or negative on each of these three intervals. And the way that we decide whether it's positive or negative on each of those intervals is we're just going to plug in a specific test point on each of these intervals. So maybe I'll test the point negative 4 and I'll test the point 0. 0 is usually a good test point. And I'll test the point 4. And by plugging those into the function f, I can see whether the function f is taking on positive or negative values on that region. So for example, if I take f evaluated at negative 4, that would be, remember f was x squared minus 9. So this would be a negative 4 squared minus 9, which is a 16 minus 9, which is 7. And notice that that's positive. So that means that on this interval here, we're going to get positive f of x values. So this region will be a positive value for f. And for the middle region, we would be plugging in an x value of 0. So this would be a 0 squared minus 9, which is a negative 9, which is negative. So this middle region will be a negative region. And then lastly, if we plug in 4, which was our test point for this right interval over here, then what we'll see is that we get a 4 squared minus 9, which is again 16 minus 9. Now here, you don't have to fully simplify your answer whenever you're plugging in these test points. All that we care about here is whether this is a positive or a negative number, because I'm just trying to determine whether this is a positive or a negative region. So if that's all that I care about, then I just need to know whether this thing ends up being a positive or a negative number. And in this case, because it's a 16 minus 9, that's clearly going to be, positive. So you could evaluate this expression fully, but if it's clear to you that this has to be a positive number, then you can immediately write the sign that you were looking for here. Now, in this case, because the function that we were looking at was just x squared minus 9, this is something that we learned how to graph early in the class. So if you just remember how to graph your polynomial like this, then we know that this goes through negative 9 as its y-intercept, and then plus or minus 3 as its x-intercepts. So we know that this function is positive over here on the left side, and then negative in between, and then positive again once it passes positive 3. And that agrees with the sign chart that we just built. But this sign chart strategy is going to be a little more general. It's going to allow us to find the regions of positivity or negativity, even whenever we don't know how to graph the original function. So that can be kind of convenient. But remember that what we were looking for was what we were looking for in step 1. and that was when is our function bigger than or equal to 0? So for my last step, I just need to use my sign chart to decide when this function will be bigger than or equal to 0, and that will be my last step here. So I'll say that f of x is bigger than or equal to 0 if x is in this region. So we have positive x values from -infinity to -3. Now, because this is a non-strict inequality, I would include the -3 as part of my interval. In other words, I'm okay with the zeros of f being included in this interval because we just wanted this non-strict inequality to be satisfied. So that's one region where f is non-negative. And then the other region where f is non-negative is this right region over here, and that would be the interval from 3 to positive infinity. And that would be our answer in this case. So we're just trying to figure out where that original inequality was satisfied, and in this case it will be satisfied as long as we plug in an x value that lives in this region down here. And for the last part of this set of notes, you'll be doing the same thing, except this time with rational expressions. So you might want to know when is 1 over x less than 0, for example. So if you wanted to solve a problem like this, we can still do it with a sign chart. But notice that, maybe let me just remind you what the graph looks like here. Notice that 1 over x doesn't have any roots, so this is 1 over x. The graph of this function does not have any roots, so it never actually crosses the x-axis, but it does change signs. It changes signs at its vertical asymptote, which is at x equals 0. So when you're applying this strategy to rational inequalities, it's important to remember that rational expressions can change signs at their roots, but also at their vertical asymptotes. So we have to look for the places where the function goes through the x-axis, which would be at a root, but we also have to worry about places where we have these vertical asymptotes. Those can both be sources of sign changes. So here, I would need to find all of the roots and vertical asymptotes. This function over here on the left side does not have any roots, but it does have a vertical asymptote at 0. So because that is an opportunity for a sign change, I'm still going to put that as sort of an anchor point on my number line. And then once I establish all of the anchor points, which are your roots or your vertical asymptotes, then you can start the plug-in strategy. And then you're just plugging in specific test values, like maybe a +1 or a -1. We're going to plug those into this left side to see whether it's a positive or a negative value. So what I'll get is, maybe let me just say f of x is equal to 1 over x. That's what we're going to plug into. If I plug in a -1, then this would be a 1 over -1, which is a negative value. So that means that this left side is a negative part on this number line. We're spitting out negative y values if we live in that left region. And similarly, if I plug in a +1, then what I would get is a 1 over +1, and that's a positive value. So that means that this right region is going to be a positive region. And then if we wanted to answer the original question, which was when is 1 over x strictly negative, then we would look at this left region over here and say that f of x is strictly negative. Maybe I'll say 1 over x is negative on the interval from -infinity up to 0. And that would be our answer in this case. Now remember that what we're doing is we're picking a test point like -1. That test point is just determining whether f of x is positive or negative on that region. It's not a division point that the sign changes at. So this -1 is not where the sign changes. The sign changes at 0, which was our division point, which we found just because that's the vertical asymptote in this case. The +1 and -1, those are just test values, and they're arbitrary. So I could have plugged in +2 and -2 instead. But I'm just plugging in values into my function to see whether that function is positive or negative on that given region. the regions being defined by those dividing values that we found at the beginning of the problem. So that's sort of the general strategy that you'll talk through. Now, I want to remind you that in the notes, you have the step-by-step procedure printed up. So I'd recommend just having that procedure in front of you as you go through the example problems. But this is the general